Oh, I'm running behind. It looks like it's time to start. Welcome back, everyone. Give me one moment and we'll get started officially. Okay, I think we can begin. Welcome back, everyone. So we're still back in section 6.5. I do have this weird issue that I want to let you know about. When I go to try to record the class, sometimes the recording doesn't work and I have to unshare the screen, then reshare it, and then the recording finally goes through. That means all the stuff I put on here has to disappear after I reshare the screen. So for the moment, this will be my solution. I'll just copy and paste it so it's available somewhere. This just looks a little bit odd. Let me know if this is kind of jarring. This is essentially in my announcements. We're still in section 6.5, but I intend to complete it today. Well, we will complete it today. It's a group effort. I also posted this calculator guide right here. So if you're working on WebAssign, doing a quiz problem and so on, or just studying, you can always go right here if you're not sure just the right order to put in the information in the calculator. And it really comes down to this. If the question is, what's the probability? You want to use normal CDF in your calculator. But if the question is, what is the value K that gets us a specific probability, like generically the 0.56, then it becomes an inverse norm function in the calculator. But honestly, between these two, it's really not as bad as it seems, because when we go to actually do a real problem, let's load one up right here. Let's suppose this was our question. We want to solve probability x is greater than k equals 0.1, like we did in the prior problem. We would set up this graph right here. And even if we forgot which function to use, normal CDF or inverse norm, this is what you could always do in your calculator. Power it on, hit second bars. And if I try to use the wrong function, the wrong one is normal CDF this time, I'll know immediately I've got a problem, because we never put an upper or lower anything on this. We put the area. So if there's no area right here, it tells us we're all not on the right track. We'd hit second bars instead. Go to inverse norm. Oh, let me fix that. I forget, if you use inverse norm here, it tries to put it as the lower bound. Let's go second and mode to quit out of there and start over. Go second bars, inverse norm. And then this is the way we can tell it's the right function. It takes an area, and that's what we were supplied. So pretty much the best way to do these kinds of problems is, if you get in the practice of doing the graph, it really tells you everything. It's going to tell you which function you have to use and what information goes into your calculator and in what order it has to go in as well. Well, that's our announcement so far for today. Other side from, we also have a new quiz posted, and this one is really just doing what we've been doing all along in section 6.5. Any last questions or comments so far, folks, before we jump back to that section? Okay, let me close this thing here. And here's where we ended up on the end of last class. So probably what we'll end up doing is finish off this problem here, and then we'll move over to section 8.2. So let's take a look at this problem. It's always a good idea, again, like I mentioned before, to read the context multiple times, really. If I was doing this as a quiz problem, I'd probably read it once just to get a feel for what's going on. Read it again, trying to pay special attention to any statistics or any population characteristics they gave us. Then maybe read it again just for good measure to make sure your conclusions make sense. But let's read through it ourselves. It says here, arsenic is a compound naturally occurring in very low concentrations, and arsenic blood concentrations in healthy individuals, we're told, are normally distributed with a mean value of 3.2 micrograms per deciliter and standard deviation of 1.5 micrograms per deciliter. They next tell us, suppose that a healthy individual is randomly selected and let X equal blood arsenic concentration for a randomly selected individual. So this information right here, I feel like this is always, if not highlighted, something to pay special attention to, maybe underline. Because once they say what X is in these kinds of problems, it now becomes really what goes into all the probability statements that we write out. When we go to give the practical interpretation, we have to recite what X is. So it's good to just keep that ready to go and highlighted. Next bit of information we have here is they told us the mean is 3.2. I believe that is a unit of micrograms. It's kind of an unfortunate symbol there. So there's a carryover in the unit, which causes confusion. The actual symbol we're going to use for this, the mean of 3.2 micrograms per deciliter, we'll write it in as mu, that's our parameter or population characteristic, 3.2, and I'll write the unit this way just to not conflate the mu as the population mean versus this as the unit. I'll just kind of do it in cursive, so it looks like it's something different. So micrograms of arsenic per deciliter, 1/10 of a liter of blood. So on average, that's how much everyone has arsenic inside your blood. And that's for the healthy individual population. Next, the standard deviation was given to be 1.5 micrograms per deciliter. This one we want to give a symbol as well, and the symbol goes like this. So here's sigma, population standard deviation, 1.5 micrograms, or hang on, yeah, that was micrograms. I missed up this unit here. I'm not super critical on units, but it's good to get them in right if we're going to try to do them at all. So micrograms here and micrograms here per deciliter. So that's the total information on this whole problem so far. Now, part A says to straight out calculate the probability that X is bigger than 7. Let's see here. Also, watch out for this statement. The graph is really the primary way that I'm giving partial credit on these kinds of problems. So we have to put this down as well for credit. So the graph for this situation, first, just do a really fast normal curve. It doesn't have to be as high detailed as we did on our last exam. I would pretty much just always just try to draw something like that. Looks like kind of a hat. 3.2 goes right in the center. And I like to get in the habit of writing these parameters off to the side, just as a reference when I go to calculate. I wouldn't say these things I'm putting down are as necessary, but if it helps you out, then decent habit. So I'll put 3.2. Sigma is 1.5. And then on the horizontal axis, X. This is the, kind of hard to fit it all in, but I'll just call this arsenic concentration. Also abbreviate concentration to concent right there. So that's our setup so far. We'll go back to the actual function they gave us. We want to calculate probability that X is greater than 7. So that's our whole question so far. Next thing we should do to our graph, place the 7 somewhere, but it's got to go pretty far to the right this time. I mean, 1.5 would take us here. That would be a 4.7. Add 1.5 again, we'd be here at about 6.2. We need to be off to 7, so it's pretty far to the right. Doesn't have to be placed perfectly, just in the relative neighborhood so that our answer we get looks believable based off the graph. So here's where 7 is in the problem. And I'll shade to the right since the answer that we're getting is this shaded area itself. So that would be my setup right before I put everything into the calculator. And if this is all you had on your graph, then I'd say that's perfect. I'm using this pen right here just as a general comment, not something you have to put on your notes, but the comments I'm putting on each of one of these is just how it's going into the calculator once you have your graph. So that lower bound 7 right here is referred to as lower in the calculator. Now my shaded area goes to the right forever. It's never stopping, going that way forever. And so we'll have to say here, the upper bound is 10 to the power of 99, putting in the largest supported integer inside our calculator. That's our approximation to infinity. And the last two things is always going to be 3 for the mean, 4 for the standard deviation. So that's our setup so far. We just have to import all that into the calculator and we'll have our probability. Let me put it equals here and let's see what we get. I forgot to, no, I did. We're rounding to 4 decimal places. And this is pretty typical for this kind of problem. So back to the calculator. The first thing we'll hit is, let's pretend we weren't here at the moment. The first thing we'll hit is second, and then the bar keys to bring up the menu. In this problem, we're going to use normal CDF because we have shaded area with the lower and the upper bound. So our lower bound will change to 7. That's where the area is going to start for our probabilities. Upper bound is 10 power 99. So put in 10. And if you forget where the power button is, I mean, if you do something like this, that's really sufficient. 10 power 99 is so overkill. It's just a way of being certain that we won't have any issues with our values. Also, it's just easier to type in than a 1 and a bunch of zeros. So let me wipe this out. Go 10. Power key is the up arrow and throw in a 99. Last bit is 3.2 for the mean, 1.5 for the standard deviation. And that's what your calculator should look like at this stage. Let me know if you're getting different values. I'm getting for this, after hitting enter once, twice, 3 times, a 0.0056. And yeah, I'd say that's believable because I put it pretty far to the right. There should be minimal area here. Even what I sketched, it looks like it would be around a couple percentage. 7 must have been even farther to the right than what we were shown. But it doesn't have to be a picture perfect graph, just enough to convey the information. Let's record for our answer, 0.0056. Sure.
So I'm hitting the second bars and then I go to number 2. But
Yeah.
every time I go into it, it's going to the first norm. Am I pushing something wrong?
So second bars, normal. Oh, weird. Let me take a
so I
look at
wanted
that.
Number 2, but every time.
Yeah, let me see how it looks there.
I don't know if I'm just missing something.
These calculators can sometimes be kind of unpredictable. We'll see that again. Yeah, that happens to me too. When this happens, we want this clear right here. Then we hit 7, and then we'll put out a 10. Now we should work in formal. We're gonna try to put that inside there. If you better. So far, we should be getting a 0.0056. Anyone else have a question on getting that number? Okay. Is that working out for you as well? Awesome. So now that we have it, we're in good shape. And that is a lot of stuff to write in and draw in. But the more you do this, the faster it goes. And really, it's just a crux so that we get pretty fluent on what goes where if you see probability X bigger than 7 and why it goes in those locations. And just a reminder, for doing these on WebAssign, the Ask My Teacher button is always a valid thing to hit. But this is the calculator guide right here. If you open this up, it's supporting both the TID3 and the TID4. I just happen to use this screenshot. It's always second bars to start. If you run through this guide, here's what it's showing. It shows exactly the function to pick, and it runs through scenarios. We didn't do this one. This is a less than scenario. It'll tell you exactly what goes into your calculator. I'd be putting in negative 10 power 99. It could be with the E or with the 10. It's meaning the same thing either way. We did this version, and that's why we have a positive 10 power 99. And we also did this version. This was example 2. If you have area between, X goes from 1 to 4. Your lower is 1, your upper is 4, and then just plug in the value for your mean standard deviation. I noticed, N32, we never use that notation in our class specifically. Let me put just a little note here, and I'm going to update this guide. This is from a class I ran about 2 semesters ago. It was through a different book. That was supposed to be the mean. That's supposed to be the standard deviation. I'll update our guide so it reflects that as well. For the moment, it's kind of janky with that problem there. But still, it goes through essentially every scenario that you might see. So if we do something like this one, probability X bigger than A, this one was an example 2. The picture should look like this, but we have to pull in the area to the left. This one gets a lot of questions. It's pretty tricky. And we're going to do this one today. If it's to the left, then we just take the probability, drop it in, and the calculator is going to be just fine with that. They'll take in the 0.15 for area, the mean, and the standard deviation. So that's our guide. Sorry, I forgot that there's a bit of a problem there. I'll get this updated and fixed. Let's now go back to this problem, and it's still not done, right? Always watch out for this right here. Now that we have a probability, we must apply a practical interpretation. And at this point, we've done quite a lot of these. It's really just exactly how it went in chapter 5. To a certain degree, that's the main purpose of chapter 5, so that we're familiar enough with probabilities, their meanings, and their interpretations. So let's begin. We can start by saying, focusing on this right here, there is a 0.56% chance that, well, something happens. We go here and we have to read off what X is. Any volunteers for what we should say next? Exactly. The arsenic. Oh, I need a article. The arsenic blood concentration for a randomly selected, and this is for healthy people. They're not being poisoned by the arsenic, so they're just fine. Healthy person is, last thing we'll say is just greater than 7 micrograms per deciliter. So greater than, or you might say more than, 7 micrograms per deciliter. So that's our interpretation there. So in other words, it looks like it's extremely rare for someone to have an arsenic blood concentration at this value and still be considered a member of the healthy population. That might be a red flag. I'm not too sure. This is definitely not medical advice. But any questions, folks, on this one here? Yeah.
So if we are only given one value for the probability, then is the upper value always going to be 10 to the 99th power?
Not always, unfortunately. For this one, the upper value is going to be 3, and the lower value is going to be negative 10 power 99.
Okay, so is the, I guess, is the missing value then always going to be 10?
Yes, 10 to the power 99, either positive or negative. And the value of it is just going to depend on, if you have a greater than, you'll expect a positive 1099. And if it's a less than, we're expecting a negative 10 to the power 99. And that's really definitely kind of confusing, right? But once we see the picture, it's really the explanation of why it is what it is, either positive or turning out negative on this one. Other questions about that so far? Okay, thanks. That's a good question about this. And really, that's the whole struggle in dealing with the calculator. I mean, it's super fast, but if we don't have a careful eye of what the situation really looks like, these are tough computations to get just right. Even people who do this all the time for a living, they often draw pictures just to make sure everything looks about the way they would expect. Probability is just sometimes a pretty confusing subject. But any tool that we can use to make it not so bad is a tool we ought to use. And the graph is really our biggest thing we have for us. So let's try it again. We want this time to calculate probability that X is less than 3. Think of X as being, once again, the blood arsenic concentration. Our graph is then going to look like this. So another really fast normal curve. Let me cite these values in case I have to scroll and I lose sight of them. I'll just continue to call this X at the moment. We'll keep in mind that we mean the arsenic concentration. So now we're taking the probability that X is less than 3. That's a tough thing to place unless we place the center at 3.2. So that's always a good first start on our graph after we've drawn the curve. 3.2 goes here. The standard deviation is quite large, 1.5. And so a value of 3, that ought to be really pretty close to 3.2. I'm not trying to place it perfectly, I'll just place it right about here. We'll throw in a light segment to cause a boundary. And now it also causes a question in a certain sense. Do I shade to the right or do we shade to the left in this problem? Good call. If it's x less 3, this is telling us to shade to the left. X greater than 7 was telling us to shade to the right. I know that, I think that's an important enough concept. Let's put it just a quick note here, because I'm never going to get the graph right without knowing which side I'm shading on. So that is saying shade to the right. And this one is saying shade to the left. So now in this problem, here's what my shading will look like, kind of low effort since it's a lot of shading this time. But there it goes. That area, whatever it is going to be the quantity we want. Now we have to remember certain things about the normal curve. These are weird things, weird facts. Total area under this is 1. That's weird on its own. But another issue is this curve doesn't ever stop. It keeps going to the left forever. And it just happens to approach the x-axis extremely rapidly at the same time. That's a pretty bad drawing. Let me try one more time on that. My axis got kind of bent. That's not helping, but it's really going to the left forever. And so when we go to analyze this problem, this is the reason why we would say for the lower boundary, it's going to be equal to negative 10 power 99. That's all because of this. We're shading to the left and we aren't stopping this time. They would have given us a number to stop on to the left here if we were. So that's our lower bound. Anyone see what the upper bound should be? It'd be the 3, absolutely, right where the area stops. So we'll say here, this is 2 for upper. Then mu is always 3. Sigma is always 4. They're always the last 2 options on all of our calculations. So that part's always helpful. So back to this calculator, let's put in the information. It'll go first, second bars. We'll probably say that a lot in this class. And if you go to normal CDF, that will work. We have a lower bound of, definitely use this negative sign. The minus sign here causes havoc in the calculator. So it's negative 10 raised to a power of 99. If I go to 10 power 99 on this, we should be getting about 1 in the calculator. Let's actually see if that happens. I'm going to fix this. It should be really 3, but this would be an interesting way to see if the calculator really gives us area 1. Yep, the calculator's decided that that's area 1. That's actually a lie, because when we stopped at negative 10 power 99 and positive 10 power 99, that wasn't the full picture. There's actual area left over there, but it is so close to 1 that the calculator cannot approximate it any differently. Now let's try to do it a little bit more correctly. Somehow my red dot disappears for no reason. Go second bars, normal CDF. This one changes to an upper bound of 3 to match the graph. And the nice thing about these problems is it stores your previous parameters, so we can just power through hitting enter now. The value we get would be 0.44770 after rounding with carry. Let me put it in as 0.44696 first. Then when we round it to the 4 decimal places, this would be the 4th. It rounds up because of the integer to the right is larger than 5. So this becomes a 0, the 6 becomes a 7, and now it's 0.4470 altogether. Does that make sense to folks on that calculation there? Awesome. Now we've got a probability. What we need to do is give the practical interpretation. It's pretty much the same thing. We just have to get the directionality right. I'm pretty much going to write out what we said on part A, but instead of saying greater than 7, I'll just say less than 3 micrograms per deciliter. So let's write out there is a 44 0.70% chance that, here I'm going to drop some of the context and just say the arsenic blood concentration it's nice to put in every bit of the context, but if we know we're talking about a healthy, randomly selected human, you don't have to say that every single time. The arsenic was definitely implying that it's coming from those people either way. Is, now we'll say here, less than 3 micrograms per deciliter. So we did it, folks. There's a huge probability this time. And looking at the value we got for the probability, it does make sense that that should be pretty close to half, since 3 is pretty close to 3.2. If it was exactly 3.2, our area would come out as exactly a half. Let's test that out just to see if the calculator knows its business. So second bars, normal CDF. Now suppose you did put in 3.2. 3.2 for our upper, it's matching the mean. Here's what you would get out instead. Comes out to, oh wow, there's a little bit of error inside there. That's kind of interesting. Should have been exactly 0.5 and no rounding whatsoever. But it's a finite machine, it can't do this perfectly. So there's a tiny bit of error in the final precision right here. Well, any questions, folks, on getting through our part B? Okay, let's try this out again. Part A, part B, we use normal CDF both times. But part C is different. The difference is here, we didn't have a probability, we were trying to find it. But in part C, we do have a probability. It's right here. So somehow, some way, this value, we need to find the right K so that the probability when X is less than K comes out as exactly 0.25, 25% of the area. All I can tell you for sure is the K value, maybe it's around here. It's got to move to the left of where the 3 was to shrink the area until it's down to a 0.25. Let's give this a try. Probability X less K equals 0.25. Our whole goal is to find the value of K. So I'll leave a placeholder question mark here for the moment. Once we find it, we'll just give a quick practical interpretation. But it's the same kind of story. We draw a curve. This one is not my best work, but it doesn't have to be pretty. 3.2 will go here. And here's the value for sigma as well. And now these are kind of tricky, but if you think about how we shaded, we're really going to try to do the same thing as well. Let me put here the area. I'll say to the left, only because it was a less than sign on this problem. Is 0.25. So I need to place the unknown quantity K. Let's make this look a little bit more important with purple. We need to place this unknown quantity K so that once we place it, the area to the left looks like it's about 25%. Right around here ought to do the job. And here's the area we were mentioning. So I'll put here, this is input 1 into the calculator, or actually let me write it this way. Area equals 0.25 is going right inside here. And just to match up what we were doing in the other problems, I'll write it this way. This is input number 1, the area. This is input number 2, the mean. And input number 3, the standard deviation. So an inverse norm problem like this one, it's not too bad. There's less things to throw in. And it's always going to be area to the left every single time we do this problem. To me, that's the kind of the confusion with it. Some people's calculators can give area to the right, but that's a little bit less common. And even the calculators that ISU is trying to use, they're trying to get a classroom set together for prior semesters. It'll be just like this one, only giving area to the left. So let's work on this one then. Our answer to finding K is found just by using this information to the right. Question first, sorry.
Sorry, so that's why like the other example that we did like this, the area that we used was like the much larger portion because it's to the left of that line, right? Like it doesn't always be the shaded part, it's just whatever to the left.
It's always area to the left, yes. Yeah, on this one, we said X greater than K, so we shaded to the right and gave it a tiny, tiny probability. Our calculator doesn't want anything to do with that. We always had to find area to the left. So we had to use the fact that total area is 1, and we just subtracted 0.01 from 1 to get that value. Does that make sense with that question there? Yeah. Awesome. I'm thinking for this current problem we're on, we have to do a part D where we do change this, make it greater than, and that could be our last one for these notes. Does that sound all right to folks? Okay, just so we can see that again, because that's trickier than this part C even. This one's nice if it's saying less than, because the thing you're putting into your calculator is the 0.25. But if it's greater than, that's not the case. Yeah, go ahead. Sounds good. That'll be our part D. Don't let me forget though. Yeah, go ahead.
So I tried yesterday, but mine is plus CD, and I used the right arrow for the one that we were in.
This one right here?
Yesterday,
Yeah.
and the answer was not the same.
Oh, that's weird. It should have come out the same.
And I double checked it, but I can show you there.
Okay, that'll work out. Yeah. Somehow, some way, it ought to work out to give you the same value of 3.23 for the answer. So we'll look into that later then. Other questions or comments so far? Okay, let's give this one a try then. So first thing we hit is, no matter what the situation, it's second bars. So second key, bars is just under your arrow keys. Now, if we try to do normal CDF, we'll just find we don't even have the information for it. We're pointed to the inverse norm. The information we do have is area. So give it the 0.25. Mean changes to 3.2. Standard deviation is a 1.5. It's a new function, so I have to re-input that information. Then enter a bunch of times, and we're on our way with this one. It says the value of K should be 2.19 after rounding to 2 decimal places. Let's put that down. But before we trust it, let's see if it even makes sense. 2.19. Let me double check the rounding on that. Yeah, it looks like that would round up to a 1.9. So what I mentioned was, once we place the K, if it doesn't seem to fit the picture, then we made a mistake. But this looks like it's about not quite a standard deviation, but it is to the left of this center at 3.2. So I would trust that that's about right for the quantity. K ought to be 2.19 micrograms per deciliter. But questions, folks, on getting that value? Is anyone getting something slightly different, or are we all ending up at around that quantity so far? Okay, sounds like we're in good shape. Next thing we have to do is give a practical interpretation. But the good news about this kind of thing is the practical interpretations, they're always about the same, whether it was a part B style question with normal CDF or a part C style question with inverse norm. I would still read it right, convert this right here into a percent chance, work on the inside, and just say what K is when I read left to right inside the probability statement. Let me get some extra space here. Oh, that's way too much. That was the one we're going to change in just a moment. So pretty much this interpretation, you could just say, let's say, find the home on the keyboard. Let's start right here with the percentage. There is a 25% chance that we have to recall what X is, but it's always good to underline it or shade it or something because it's going to come up repeatedly. X is the blood arsenic concentration. We'll say there's a 25% chance that the blood arsenic concentration, I'll just say here, literally is less than, since it's a less than sign, is less than. Then we just cite the value 2.19 micrograms per deciliter. And that finishes off the entire interpretation on this one. Be sure when you give this kind of interpretation that if there's a directionality on the statement, we have to have a directionality on it as well to match up with our interpretation. We could say below 2.19 milligrams per deciliter, micrograms rather, that's a strange unit, or anything other, but it has to convey the direction of below. Well, that's a second one down, and let's change this problem a little bit. This one's brand new, so I'll put this in red just to communicate it wasn't originally on the notes, but now it is. Let's change this to a greater than K. And we can put any probability here between 0 and 1. Any volunteers for your favorite probability? How about a 4? This nice, well, we already did a 4. That was the 0.25. How about something just random? 0.8349. Weird random problem, but that is a bona fide probability, right? So we can answer the question in this one. So probability X greater than K is this random probability, and same instructions as before. Let me just recopy it so we can use our own handwriting on this. Probability X greater than, this is the value we're trying to solve, K, equals 0.8349. Now, here's the way I would typically answer this kind of question. First, let me put down a personal reminder that we need to come back and fill in the value of K, but let's now throw down a graph much like the one above. That one is a slight improvement, but not by much. Let's put in the center because that's always a good check on our work. Okay, so finally, that's our whole graph. Now let's analyze the situation just a little bit closer. The greater than case says the area. Now this time it's not to the left. We only said to the left because of the left hand sign there. The area to the right is 0.8349. So if the area to the right of wherever K is really large, K couldn't have even been here. By that red dot, the area to the right is exactly 0.5. I need to start putting it maybe around this area once again. It needs to be somewhere around here, maybe even further than the left in the last one. So here's where I'll place K. And now let's put in that area. The area to the right of K was 0.8349. Now, some calculators, I think a couple people in the class, you can select the area to the right, give this value as your first input, the mu and the sigma, and our answers should match up, but we'll test that in just a moment. For most calculators, again, the mantra for this is it's area to the left always, no matter what, when it's an inverse NOR problem. Let's put a big comment on this one. The area to the left of 0.8, or excuse me, not to the left of the value there, to the left of the K. I forgot to actually write in K when I put in that line. The area to the left of K, that's a little bit better now, it'll be 1 minus the supplied area. And this is because the total area is always exactly 1. So 1 minus 0.8349. And this will be the area we actually used. So back to the calculator for just a small amount of time. 1 minus 0.8349 gives us this figure, 0.1651. And that's the actual area that our calculator would be taking on this problem. I'll highlight that just to signify we're using this area. And now here's the organization in the calculator. Here's input 1, area. Then this is our input 2 and our input 3. So now we should be in business with this one. Let's see what it comes out as. Hit second bars. Inverse norm will take the area and we'll give it 0.1651. Now notice this is a really confusing question because if I saw this as say a quiz problem or something and I saw greater than K, I'm probably immediately putting in 0.8349. That just looks like the right thing to throw in, but per the graph, it's not quite right. We're really putting in 0.1651. Mu and sigma are set and correct. Good to double check. And here's how we're getting what we're getting on this value. I've got a 0.17394 altogether. This one's rounded to 2 decimal places, 0.17394. So we'll say K is rounded to, let's see, to 2 decimal places. This one will round down. Yeah, go ahead. Oh, yeah. I've been having that struggle lately. I keep saying it one way, then messing up my decimal. Sorry about that. That was totally me. Sorry about that. Let me try to fix this. I need to be a little bit more careful with my decimal numbers there. I think it's when I try to put in a 0 point, and then sometimes I don't put it in. It kind of messes me up. It was a 1.7394. Thanks for spotting that. 1.739, which will totally change our rounding on this one. To 2 decimal places, we'll round up to 1.74. Now that we have that value, we look at the graph, and yeah, that's very plausible. It's far to the left of 3.2, and there is not very much probability to the left. So it should have been even further than this K was at 2.19. So that should be our value right here. Did that work out for you with using the right tail?
Yeah.
Oh, glad to hear that. Maybe I put my decimal point in the wrong place just right here. Tiny little mistakes like that could cause it, yeah.
It was, well,
Gotcha. Well, other questions or comments, folks, on getting to this stage? Okay, we still have a practical interpretation to go, so let's put that down on paper. Now, I've been doing these in a certain style that always works. It becomes a process. If you want to get a little fancy on these, you could change it up. Let me show you what I mean by that. On part D, a bona fide practical interpretation could go like this. There is a 83.49% chance, or hang on, that's going to be the same interpretation, isn't it? Sorry, let me try one more time. I guess I just like interpreting it that way. You can always say there's an 83.49% chance that the blood arsenic concentration is greater than 1.74 milligrams per deciliter. But you could also say 83.49% of individuals in this population have a blood arsenic concentration of 1.74 milligrams per deciliter, or, oh, that was weird. It scrolled right when I was writing. Or because of the greater than sign, we'll say more or higher is probably the better way to say this, or higher. Essentially, it's not any too different than the interpretation above, but it's focusing more on just talking about the percentage of a whole population rather than saying select one and have a 25% chance of something happening. So I only wrote it out this second version just to say it doesn't have to be exactly the way we write it. If you find another way to convey the same information, that's always completely fine as well, as long as it captures the statement. Yeah, go ahead.
So like, I guess the way that it's written out there is kind of confusing because it doesn't have like the equal sign under the greater than sign. Because in this one it says like a concentration of 1.74 or higher. So it would be like just higher than, like just greater than 1.74. Like it can still be equal to 1.74.
Yeah, this one is conveying it could be equal to 1.74, and this one's conveying it's strictly below. But the reason that that's not as much of an issue is one weird fact about the normal distribution. You might have noticed we have never calculated this. That's really weird, right? Every time we calculated with the normal distribution, we insisted we had a range of values, like say, X is from 3 to 7, or X is bigger than 7 or less than 5. But if you put in one specific answer, this is the weirdest probability of them all. This doesn't come up a lot, so this is a great question. Anyone happen to know what that would turn into as a probability?
Just be that point.
It wouldn't be the point, no. It has to be some number between 0 and 1 to be a specific probability. But let's see if we can draw this out just to see what would happen. And then this should answer your question. Let me know if it doesn't though. So if I were to try to answer this question, this is what I would draw. I would put in, forgetting my values, but I believe mu is 3.2, sigma is 1.5, but those are less important about the situation. It's really the strict equality here, which is getting to your issue because of the less than versus less than or equal, right? So I'm going to put my 3.2 here. I'm going to put the 1.74 right here. And now the question is, which way would you shade if you had to shade? I would definitely put a line, right? Like before. I think that's still appropriate. But I can't shade to the right or to the left because I want the probability X is 1.74, not a shy bit more or a few bits less. Exactly that quantity. That would make 1.74 both the lower and the upper. So let's put that in. This is input 1 for lower. This is also input 2 for upper. Then here's input 3, here's input 4. And now let's try to put this back into the calculator. So this is a really weird probability, but we'll see what it comes out as. Go second bars. This is a normal CDF problem still. Lower is 1.74. Upper 1.74. And I should change these, but I really don't have to. My claim is that the probability is 0, no matter what we put here. But let's put them in, 3.2, 1.5, crank it out, and it's definitely probability 0. So here is a really weird situation about these kinds of probability models. The probability of a single point emerging is null. It's always 0 whatsoever. And that means back in this problem, you could have wrote probability X greater than K, or you could have wrote probability X greater than or equal to K, and it's the same exact value because the or equal portion doesn't even change the probability. So whenever you give interpretations, you are welcome to imply it actually takes on 1.73 and higher, or you can just imply it's strictly below 2.19. Whether you include 2.19 or exclude it, one way or another in your interpretation, both are considered perfectly acceptable answers. In fact, mathematically, they're both 100% correct. Probability is just a weird science. It always comes out 0 for this statement. let's say that as just a final mention. Probability X equals K is always 0 for the normal distribution. If we were in a normal probability, say in chapter 5, yeah, X could take on a specific value, but here it's got to be a range. And the reason, again, is also recall probabilities are areas. There's no area here, it's just a line, it's one-dimensional. There's no concept of area for a line here. We have to shade in order to produce an area to get something non-zero in this location. But thanks for asking that question. That's a really technical but important question, and it matters in these interpretations. Well, now we know it actually doesn't matter. You can imply either way. Well, any last questions, folks, before we call tonight? Okay, I think I got sidetracked. I talked a minute over. Sorry about that. I'll return the balance next class somehow. But when we come back on Tuesday, we'll be in section 8.2.
Yeah, that's Monday.
Did I say Tuesday? Sorry about that. I have a Tuesday, Thursday class. We will be back on Monday. Sorry about that.